Right, question 3. Velocity time graph given for a body accelerating in a straight line. We've got the usual symbols here: initial velocity, final velocity, time taken. Using the symbols on the graph, write an expression for the gradient and state what it represents. So gradient, change in y divided by change in x, so that's v minus u is the change in y. Change in x is just the time taken t, and that is equal to the acceleration. Remember, gradient of a velocity time graph gives you acceleration. Using these symbols given on the graph, write an expression for the area under the graph. So if we look at this graph, we can see it's a trapezium. The parallel sides are of size u and v, and the base is of size t. So area of a trapezium is just a half u plus v, because that's the average of the two sides, multiplied by t, and that is equal to displacement. Hence or otherwise, show clearly using the usual symbols x equals ut plus a half at squared. So from our previous answer, we can write that x is a half u plus v times t. And from the answer before that, we have that a is equal to v minus u over t. A quick rearrange gives v equals u plus at. So substituting this into here, I can write x equals a half u plus at times t. So that's a half of 2u plus at times t, which is equal to ut plus a half at squared as required. So cyclist accelerates from rest, constant acceleration of 0.5 for 12 seconds. Calculate distance traveled in this time. So we can just use the formula that we've just derived. X equals ut plus a half at squared. U is equal to 0 because we're starting from rest. And then it's just plug in the numbers. A half times 0.5 times 12 squared, which I suspect is equal to 36 meters. Calculate then the maximum velocity attained. We're starting from rest. We have a time, we have an acceleration, so we can just use v equals u plus at. Again, u is equal to 0, so it's 0 plus 0.5 multiplied by 12 to give me 6 meters per second. So this next part C, after 12 seconds, we're stopping pedaling, freewheeling to a standstill. So to a standstill implies the final velocity is 0 with a constant deceleration, and we've got this distance of 120. Calculate the time taken. So if I look back up here a little bit, we can see that this expression, a half u plus v t, is going to give us all the details we need. So plugging in the numbers, I've got 120 meters equals a half initial velocity. We calculated as 6 meters per second. Final velocity 0. T is what we're trying to find, so t is therefore equal to 120 over 3, which is 40 seconds. Calculate then the magnitude of the cyclist's deceleration. I don't like the word deceleration, but I'll let them off with it. We've got this, a equals v minus u over t. The change in velocity here is 6 meters per second. Well, technically 0 minus 6 over the time taken, which is 40. So that gives me an answer of minus 0.15 meters per second squared. I'm only interested in the magnitude, so the minus sign is neither here nor there. So I guess my final answer is just 0.15 meters per second squared. Slightly unusual question this, because it's asked for an acceleration time graph for the whole of the cyclist's journey. So this shouldn't be too taxing. We've got two constant accelerations. So cyclist starts from rest and has this initial constant acceleration of 0.5 meters per second for 12 seconds. So that initial acceleration is going to be positive at 0.5 and it's going to last for 12 seconds. Then after that time, we have this negative acceleration of minus 0.15 and that lasts for 40 seconds. So this grid below, the first thing we need is an x-axis. I'm sure I could manage to find a ruler or something, but I'm not gonna. So this is time, and we'll have acceleration in meters per second squared on the side, time in seconds. We're going to need an appropriate sort of scale for this time axis. So the total sort of journey time here is 52 seconds. So if I go up in tens, that should give me enough room. And my scale for the acceleration, I need a positive acceleration of 0.5, negative 0.15. So if I call this 0.5, this 0.25, 0, minus 0.25, and minus 0.5. That initial acceleration then, lasting for 12 seconds, gets me to here, and that's a horizontal line. Sorry if that's not very clear to see. And then at this point we stop pedaling and the acceleration becomes minus 0.15, which, let's see, is somewhere about there. So we've got this instant change of acceleration, and then that is maintained for the remainder of the journey time, which gets me as far as 52 seconds. And that's as far as we go. So let's gonna have a careful read of this next part of the question. We've got total resistive force acting on the cyclist with a constant frictional force and an air resistance force which is proportional to the square of the cyclist's velocity. So this constant friction force is 8 newtons. So when the cyclist is traveling maximum velocity, and remind ourselves that that maximum velocity was 6 meters per second from this question, the total resistive force acting was 165 newtons. Calculate the force of air resistance at this velocity. So the frictional force is constant. So if the total resistive force was 165, we can just subtract the constant frictional force from that to get the air resistance force. Hence calculate the total resistive force acting when the cyclist is moving at half the maximum velocity. So this air resistance force is proportional to the square of the cyclist's velocity. So if I half the velocity, that is 1/4 of the resistive force, because it's a half squared. So that would give me the air resistance force. Then I need to add back in the constant frictional force of 8 newtons. And I'll plug that one into the calculator. Which gives me 47.25, and I'm going to give my answer to two significant figures because everything else here is to two sig figs. So 47 newtons. Question 3 done.